Hello everyone, and welcome to this video. Today we're going to be talking about one of the most fundamental concepts in analysis, in fact the most fundamental idea, which is that of continuity. And if our endeavor is going to be more intuition inclined, then it is safe to say that continuity captures the idea of preserving nearby points. And the fact that this idea can be expressed in a meaningful fashion in the metric space setting is one of the main reasons that the concept of metric spaces is so useful in analysis. In the possibility of so extending the concept of continuity, to topological spaces, or be carried over successfully to functions from one arbitrary topological space to another, already begins to show how appropriate the idea of a topological space is as a generalization of metric spaces. And we will see in a much more advanced territory how, in a much more of a meta lens in mathematics, in the context of category theory, continuous functions are basically the morphisms of topological spaces. When we say a function is continuous at a point, it means that for any small open neighborhood around that point, the function f, in this case, maps that neighborhood to a set where the corresponding points are also close together. So in this sketch, let's say, the small open neighborhood, we are basically describing this within the context or within the language of a metric space. And the small open neighborhood is, in this case, the open ball centered at x with radius alpha. And basically, the function maps this neighborhood, this open ball, let's say, to a set where the corresponding points, in this case, it is the image of this open ball, the corresponding points are also close together. So basically, it is a conservation of the notion of nearness between the points or within the neighborhood of this point. We can say even the function doesn't introduce any sudden jumps, breaks, or abrupt changes in values as we move through nearby points. And side note about this sketch, this is all for understanding purposes. I know how diagrams can be most of the time misleading, especially in math, since diagrams do not really encapsulate all manifestations of a certain property. So yeah, this is only to internalize the concept. In order to formalize this definition, we would take f function from the open subset u of x to y, and we basically say that f is continuous at x in u if for every open ball b of y centered at the image of x with radius epsilon, there exists an open ball in x centered at x with radius alpha, such that, of course, this is contained in the open subset U, such that, and this is the crucial part, that the image of this open ball, it is contained in the open ball centered at the image of x with radius epsilon. This is very interesting because it sort of draw this imagery of overlappment. So basically, the image of x is of course the same in both cases. So this is the f of x. That what I mean by this, that f of x belongs to this, which is the most certain common element between these two sets. And what this shows basically is the neighborhood of, or how basically the neighborhood of x, it is mapped by f which highlights the continuity property very beautifully. Now, as I said, I'm going to highlight these key terms because they would come very, very crucial in other formalizations of continuity, and which it will lead us, or we will circle back to a very foundational definition of continuity, which we all encountered, which is the epsilon delta definition. And basically, in an equivalent manner, also, we can say that f is continuous, excuse my handwriting, at given point x of u if, and I'm definitely going to change the color to highlight that for every epsilon that is positive that exists in alpha, such that for whatever y in the same open subset u. We can describe this in terms of metrics, like a metric, but it's the same thing if we would describe it using a norm or any notion of distance. Really, it is preserved. So basically, if we say, if we describe it in terms of open ball, this is the set that is equivalent to, say, the distance between x and y. It is indeed inferior to alpha or equal. Then we described y by delta, metric delta. Let's say that the f of x, f of y, it is inferior or equal to epsilon, which is equivalent to the definition that we have seen earlier. Now, continuity ensures, in a literal reading of this statement, ensures that small changes in the input basically results in small changes in the output. Okay. Now we're going to talk about continuity within the settings of topological space. And continuity is typically defined using the concept of open sets. And an open set, which actually validated the previous formalization of continuity, is a set that basically contain an open neighborhood around each of its points. And intuitively, an open set allows for small perturbations around each point within the set. Now, formally, f from x to y, given that x and y are two topological spaces, is continuous at x of x if for every, and again, we're repeating the same keywords, every open set V in Y, such that the image of X is in V, there exists an open set U in X, such that terrible handwriting, I am so sorry for that, such that X is in U, and of course the image of this open set is contained in V. This is trivially equivalent to our former definitions, and you can pretty much acknowledge the underlying similarity between all of these formalizations. They converge within the same notion and essence, which is that of the nearness of the neighborhoods of a point within a given space that has some sort of a structure which is capable to describe um, distance or any form of closeness. Um, so the notion of continuity is important because it really aligns with our intuition about smooth and well behaved functions. For example, if you have a function, a continuous function representing the temperature distribution in a room, you would expect that small changes in position within the room would result in small changes in temperature. If there were any sudden jumps or discontinuity in the function, it wouldn't accurately capture the physical reality. Um, so, this is it for this video. I hope I was able to deliver some degree of knowledge, or I was able to help you capture the beauty of this property, which is that of continuity. And in the next video, we're gonna continue our journey with continuity, but we're gonna elaborate on how continuity interplay with other notions like sequences and how we carry continuous functions from topological spaces and metric spaces, um, and much more. But for now, thank you for your time and have a great day.